Hello, in this video we'll be discussing section 1 of chapter 4, motions in 2 dimensions. Let's use this example that we see to the right to start our discussion about motions in 2 dimension. This particular diagram shows a trajectory of some particle or some object moving through space. We're imagining that we have some extended object and we're using our particle model to reduce it to a single point. We've defined a coordinate system, our XY coordinate system here. This object is following this curved path, its trajectory in this particular plane. What physical things can we describe about this object? We can first of all locate the particle in terms of a position vector that we'll call r hat. That position vector just starts from the origin and points to the position of an object at a specific instance in time. So for instance, at this point, this object, at this time, this object is here. And it has a position vector that starts at the origin and has some direction and size that tells me where that object is in my coordinate system. Okay. Because now I have a two-dimensional vector and a coordinate system, I can describe that position vector in terms of its vector components. Vector Rx, the vector that points in the x direction, that is the magnitude, right, that spans the position vector in x, and vector Ry that points in this positive direction, such that when I add Rx to Ry, I get vector R. I can use my unit vector notation to write this position vector R as xi hat plus yj hat. If I then look at an object at two different times along this trajectory, right? Here I see at some time that we'll call t1, this object is at position r1. At some later time t2, this object is at position r2. You can see vectors r1 and r2 are the position vectors that describe the position in this particular coordinate system of this object at those given times. I could then ask, well, what is the displacement vector, delta r, in this particular example? Okay. Delta r is a vector that describes how my object has moved as time has advanced. Delta r is just r2 minus r1. Okay? r2 minus r1. Notice, remember, vector negative r1 points in this opposite direction. So if I take r2 minus r1, I'm going to get this vector delta r that points in this direction. Also notice that delta r, I can write it down in terms of its component vectors. It also has an x component and a y component. And in this case, using the properties that we described in the previous chapter, since I'm taking a vector difference, the x component is just the difference in the x components between r2 and r1, and the y component is just the difference in the y components of r2 and r1. Okay. Let's look real quickly. Let's grab our pen and draw that here. So for instance, if I'm looking to draw Rx, it's going to be this vector that spans R1, spans from R1, the origin, down to here. So here's my Rx vector, R1x. Okay. So this would be R1x. What about for R2? Well, I can define another vector that goes from my origin over here to the tip of R2, and this will be my x component of R2. So here's R2x. Okay. Now I want to take the vector difference, so I want to take vector R2x and subtract R1x. Here's R2x. Here's minus R1x, something like this. Negative R1x, it points in the opposite direction. So the resulting vector then is this vector that points in, right? Let me grab a different color quickly. Let me grab the green. That vector difference then is this green vector that goes from the tail of R2x to the tip of minus R1x. Okay. And notice that that's going to match the component, right, the x component of my delta R vector here. Okay. So these two vectors here would end up being equivalent. And I could do this similar exercise in the y direction. What other physical quantities can I describe? Well, now that I've defined my delta R, right, my displacement vector delta R, I can also describe an average velocity. The average velocity is just that delta R vector divided by the time interval, the time that it took me to get from position 1 to position 2. Okay. I can also write that down into vector components. Notice that, right, if I look at the vector components for R, if I divide that by delta t, notice this is just a scalar quantity. This is not a vector quantity. And so if I use my rules that we saw last chapter, that just scales each individual component in the same way. So I just scale the x component, scale the y component, and right, I have units associated with these things, right? Say I measured in meters here and in seconds, so each of these would have units like meters per second and give me the velocity vector that points in the correct direction. What about instantaneous velocity? What do we mean when we talk about the instantaneous velocity of some object moving in 2 dimensions? In that previous example, right, we were talking about the average velocity. Why is it the average velocity? Because, right, we know something about the position at this time and some later time, but all along the way that object was moving and its velocity could be changed. So this vector represents the average velocity as it moved from 1 to 2. Well, what if I want to talk about the velocity of an object that's happening in 2 dimensions at a very specific point? Okay. Just like we saw in the 1-dimensional case, the instantaneous velocity is the limit of that average velocity as I run delta t down to 0. Right? If I keep shrinking this time interval down to smaller and smaller values, then I get that v, the instantaneous velocity, is this limit of delta r of t as I shrink t to 0. Okay. Mathematically, we can describe that as a derivative. The velocity vector is the time derivative of my position vector. Sorry, my displacement vector here, my position vector here. And this is just equivalent, right? I can break this up in terms of components. It's the time derivative of the x component and the time derivative of the y component, right? Multiplied by their unit vectors and summed together. We can write this simply as that velocity is just equal to vxi times vyi, where the velocity in the x direction, right? So now I'm breaking that velocity vector up into its components. There's an x component to the velocity, right? The component of this velocity vector that points in the x direction. And that's just equal to the x direction, right? The time derivative of x. And in the y direction, I have a similar case here. If the velocity vector's angle, that we say call theta, is measured from the positive x direction, then we can say that the velocity components here are just equal to v cosine theta, and the x component of the velocity is equal to v sine theta. And I can find the speed or the magnitude of that velocity vector by just using the Pythagorean theorem or taking the square root of the sum of the squares of the components of that vector. We can also use this conversely to find, say, that angle. If I knew the velocity components, I could just find that that angle with respect to the positive x direction would be inverse tangent of the ratio of vy to vx. So this is just using, right, once we have the velocity vector sitting on a coordinate system, I can decompose it and I can use my geometrical representation that we described in the previous chapter. We can continue this line of thinking, right? What about the acceleration? Well, the average acceleration of an object moving through some two-dimensional space is just going to be the change in that velocity vector, right? Some v2 at some initial time minus some v1 at some later time divided by that time interval that between those two points. The acceleration a points in the same direction as delta v. That's going to lead into a change in the velocity, right? So accelerations change the velocity. As an object moves, its velocity vector can change in two different ways, right? Now that I have two dimensions, the magnitude of my velocity vector can be changing, right? It can be speeding up or slowing down. I can change the speed. But also I can change the direction of that velocity vector. So this delta v can come about from either one of these or both simultaneously. I can have a velocity vector changing in magnitude or direction. And in either case, I have an acceleration. So if I have two velocity vectors here, say vi and vf, I can find the acceleration vector by the average acceleration by placing, right, taking those velocity differences. So here's vf. I add to it minus vi. I'm going to take vf minus vi. Once I have that, I can find delta v here, and I can see that the acceleration, right, is going to be this delta v divided by the time interval. And so the acceleration is going to point in the same direction as that delta v. Remember that delta t, that time interval, is just a positive scalar that I'm going to use to get the correct units and size of that acceleration vector. Now that I have an acceleration vector, well, I can place that vector into my coordinate system. And let me think about just using a coordinate system where I'm going to imagine lining one direction along, right? I can always rotate my coordinate system. I'm going to define a parallel direction that's aligned with my velocity, and I'm going to say have a y direction that's perpendicular to that velocity. So I can think about a component, right, a direction that's parallel to my velocity and perpendicular to my velocity. And if I have that kind of coordinate system, well, then I can decompose that acceleration vector just like any other vector into its vector components. One component that's parallel to v, one component that's perpendicular to v. What do these two different components do? The parallel component is the piece of the acceleration that changes an object's speed. Okay. If I have a component of acceleration that's parallel to v, it's going to, if they're aligned, then it's going to cause the object to speed up. If they're anti-aligned, the object will lose magnitude or slow down or change direction. A perpendicular component is the component of the acceleration that's responsible for changing the object's direction. Okay. An object that's changing direction always has a component of acceleration perpendicular to the direction of motion. So the average acceleration is found from those two velocity vectors separated by some time interval t. If we want to get to the instantaneous acceleration, we do the same thing we did for the velocity. We shrink delta t to smaller and smaller values until that delta t runs to 0, and the result is an instantaneous acceleration at the same point on the trajectory as the instantaneous velocity measured. What does it look like? The figure to the right shows the trajectory of a particle moving in the xy plane. Here this vector is drawn, this velocity vector is drawn at this specific point and represents the instantaneous velocity of this object, and vector A is representing the instantaneous acceleration. We can decompose that acceleration into components that are parallel and perpendicular to the velocity. And we can see in this case, this acceleration will be slowing down, right? It points in the opposite direction to the velocity, so it's going to be taking away that magnitude of velocity. and also it's going to be turning that velocity towards, it rotates this vector towards that applied perpendicular acceleration. So this particular acceleration will simultaneously be changing the direction and magnitude of my instant of that velocity v as time progresses. Notice something here, that in that previous example I had an xy coordinate system initially that is aligned, say, with maybe this is the horizontal, this is the ground, and this is the direction that something like gravity points, that's perpendicular to that direction. In order to understand how these accelerations are working, we want to think about a rotated coordinate system that's aligned with v, that has one component parallel to v and one that's perpendicular to v. Why is that? Because if I use this x and y, I can see here the figure to the right shows vector A, but now decomposed into my original x and y components. I can also decompose my acceleration in this coordinate system. Here I have a vector ax that points backwards and a vector ay that points down. Remember that total vector A just came from taking that limit as I shrink to 0. That just gives us the derivatives here, time derivatives, and so the individual components of ax are just the time derivatives of vx at that instance in time. So if I have an acceleration that's decomposed in some coordinate system as ax and ay, ax I hat plus ay j hat, and say that acceleration is constant, so it's fixed and it's not changing with time, then the two components ay and ax are going to stay the same throughout a problem. In this case, everything from chapter 2 that we saw about constant accelerations applies for the individual components. We just have two sets, I can write down, just if I get rid of the y component, I have just what we saw in chapter 2, that I can find the new x component if I know the initial velocity, initial x position, and that constant acceleration and the time interval. And I can also find the final velocity if I know the initial velocity condition in the x direction and the constant acceleration in the time interval. And then I have an identical copy in y. So I have these two systems where I've decomposed everything into x components and the y components. And what's happening in x is just following its own set of kinematic equations from what's happening in y, What's happening in x is happening independently but simultaneously from what's happening in y. The thing that ties these two together is the same time interval has to be elapsing as the system moves on, but they can have independent accelerations in each direction, independent initial velocities in each direction, positions, etc. Okay, that ends our discussion of this section of chapter 4. Thank you very much.